This is part 6 of Roger Klang's Actual Philosophy from my book Causation and the Universe: A Bridge Between the 1900s and the 2000s. Also, the philosopher Bertrand Russell addressed the self-contradictory logical problems one can construct with linguistics and set up in an equally contradictory theorem in Russell's paradox or performative contradiction. The paradox is as follows. When people say, all truths are relative, they make an absolute claim, and thus it becomes a contradiction in terms. I can answer with saying that if all truths are relative, they are not truths. They are but a mishmash or a composite of separate truths and non-truths, and/or a mishmash in the interpretation of the meaning of different non-hyphenated, usually, words that need to be figured out separately, just like I did with the suggested variants of Gödel's incompleteness theorem. Either the truth, or in other words, the claim, is true, or it is false, but it cannot be half true in between. An example of Russell's paradox is the following. A male barber in a village shaves all the men in the village who do not shave themselves. The question is, does the barber shave himself? If the barber shaves himself, the claim that the barber shaves a man who shaves himself must go against the definitions, and therefore he cannot shave himself. But if the barber does not shave himself, he is a man who does not shave himself, and consequently he must be shaved by the barber. So the barber must shave himself. This contradiction is Russell's paradox. I personally look at the paradox in the following manner. The barber represents the answer to a math problem. The answer A should not be part of the calculation. It should be the result of the equation. Let us call the answer, i.e. the male barber, A. And let us call every man in the village whom the barber shaves, small a, or lowercase a. The rest of the male population in the village shave themselves. Let us call them lowercase b. A represents not the barber, but the total number of shaved men. Because why would you say that A is a person when lowercase a is the number of men that gets shaved and lowercase b is the number of men that shaves themselves? It's just numbers. I know, it's confusing. But it is because Russell's setup is illogical. But we thus get the formula A equals lowercase a plus lowercase b. Suppose now that we rearrange the composition into A minus lowercase a equals lowercase b. Or A minus lowercase b equals lowercase a. A is the total number. If we subtract a from lowercase a from a, we get the number of men who shave themselves. If we subtract lowercase b from a, we get the number of men who get shaved by a. This is simple math, and not a story about a barber. The result cannot be about whether a barber shaves himself or not, because that results in inconsistencies. Two of them being that lowercase a and lowercase b cannot be numbers if the answer a is not a total number added from lowercase a and lowercase b. That's it. It is not really a conundrum. But let us set up the equation wholly infallible according to Russell's paradox by starting with the barber A and assume that he gets shaved by the barber A, i.e. himself. As before, lowercase a is the number of men that gets shaved and b, lowercase b, is the number of men that shaves themselves. A plus lowercase a minus lowercase b equals a. Or in other words, a equals a plus lowercase a minus lowercase b. Barber A gets shaved, depending on how you look at it, and so are a portion of the villagers, lowercase a, shaved by him. So he appears twice in the equation. Thus we would get the absurd situation where the result a and the barber A becomes a factor on both sides of the equal sign. And then again, they don't, because the A on the long side of the lineup represents a single barber that shaves the barber. While on the short side, we have the total number of shaved men by the barber. Except we don't get a correct result from this equation, since it is not a valid equation. Now let us assume that the barber A shaves himself. A plus lowercase b minus lowercase a equals a. Or in other words, a equals a plus lowercase b minus lowercase a. Here we get the same paradoxical situation, since a is one of the men that shaves himself. So what does this faulty math tell us? It tells us that the total result a on the short side of the equal sign would presuppose the result in the equation on the long side of the equal sign. That means that you will have the total number of shaved men called a on both sides of the equation. A should then equal a plus lowercase b minus lowercase a. Except you won't, since a shaves himself and adds to lowercase b, who all shave themselves. And thus the remainder gets shaved. So you subtract lowercase a and get a. The math lineup is incorrect, since it doesn't add up, and you should not be upset over the bad math. The German mathematician David Hilbert, born 1862, deceased 1943, who confessed to the formalists as opposed to the intuitionists, set up to prove that mathematics was both a. complete, meaning, does every true statement have a proof? If yes, then mathematics is complete. And b. consistent, meaning, is it free of contradictions, or contrary? Can you prove both a and not a simultaneously? If you can prove both a and not a simultaneously, then mathematics is not consistent. And finally, c. decidable, meaning, is there an algorithm that can always determine whether a statement follows from the axioms? If yes, then mathematics is decidable. Kurt Gödel, born 1906, deceased 1978, was thought to once and for all have proven that the first mentioned postulate A can be considered to be incomplete, and that mathematics at best is questionable, partly contradicting the second postulate B. Alan Turing, born 1912, deceased 1954, was thought to have proven that mathematics is undecidable, contradicting the third postulate C. Alan Turing was presumably right in that mathematics is undecidable, albeit this might only apply in the quantum world, but stepping up in the macro world as a bug, that is why the Turing machine was not so useful in answering Hilbert's question on decidability. If, and only if, there is only supposed to be one possible macroscopic outcome based on the input to each singular step in a digital linear computer with a read-write head that can read one digit at a time and that can perform one of only a few tasks. Even though Turing's computer machine has large electronic components, it might not be in the macro world that the computer operation bug emerges. It just pops up there. Same thing? Let me give you another example of a quantum bug jumping up in the macro world. In May 2003, voters in Belgium went to the polls. Often the municipalities provided a computer for voting. One of them was in Schaerbeek in central Brussels. One of the politicians in Schaerbeek received more votes than mathematically possible. Luckily, they could recount the magnetic voter cards manually by inserting them into the voting machine. This time, the outcome looked much more correct, and the opted-for politician received 4,000 less votes. They meticulously searched through the code but couldn't find any bugs. They tested the hardware, but again, they could not find any errors at all. The exact number of votes for this politician in the first instance was 4,096. What happened was that the 13th binary bit flipped from a 0 to a 1 for no apparent reason. What is remarkable about the number 4096 is that it is exactly a power of 2, or 2 to the power of 12. That is the 13th bit. The funny thing is that they counted the votes exactly in the same way the second time and got the correct number of votes, as opposed to the first time. Was it a quantum bug stepping up in the macro world, or was it a cosmic ray kinetically flipping the bit from a 0 to a 1? We can only receive an answer if we reconstruct the Turing machine and run it till a bug appears. But it is weird that the bug in the voting computer manifested itself the way it did if it was caused by a cosmic ray. But Kurt Gödel, I assert, was wrong in that mathematics would be incomplete outside of the quantum realm, Rogers note. What is the point with mathematics if it is both incomplete, inconsistent, and undecidable? If it were, we would not have been able to make any sense of it as a tool at all. Author Roger Clang, updated version 23rd of May 2021, first translated into English in 2011.